All right, so last time we talked about vectors. One thing that I should have done but failed to was to specify the symbol for the magnitude of. So sometimes we will write the magnitude of a vector just like this, omitting the little arrow sign. And other times we'll be a little more explicit and use this kind of absolute value indicator around the vector. We talked about tip to tail addition, components, and you've had more practice with components on the homework. And we talked a little bit about the velocity. And as you saw on the homework, that we could define the velocity vector to be, so the average velocity would be the change in position divided by the change in time. So hopefully you've already been using that for one or two of the homework problems. And then we talked about relative motion. So typically this applies to things moving within a fluid medium, but like air or water, but also there are other circumstances like somebody moving in a train that's moving, for example. And we used our intuition to get this equation that here I've done things sort of schematically rather than with respect to a particular problem, that the velocity of A relative to C is the velocity of A relative to B plus the velocity of B relative to C. Questions about any of that? Okay, so don't forget today, yes, Alex.
Isn't that speed with direction is a vector though?
Yes.
So why is a vector with nine? Oh, never mind. That makes
Okay.
sense.
Yeah, no, it's a funny way that I wrote that sentence. So remember that your homework is due at 4 p.m. today. It must be in PDF form. It must be in PDF form. Otherwise, it causes too much extra work for me and the graders. And you must turn it in on Moodle. There will be our assignment number 2 will be due next week at 4, and I will post that a little bit later today. For those of you who just got here, a reminder that you do have lab next week. So make sure to do the pre-lab reading, watch the pre-lab video, be fully prepared for it so that you can fully support your partner and not slow them down. So I think that's it. Okay, when we left off, we were in the midst of this concept test about hurricanes. So we were thinking about a hurricane that is moving with the velocity to the center relative to the ground, C relative to ground, going northwards. And in the northern hemisphere, the circulation of the hurricane is counterclockwise. So the velocity of the right side relative to the center is like this, velocity of the left side relative to the center is like this. And the question is, why is there more damage due to wind on the right side, so along this area of the coast, than there is on the left side? So we've had a good long while to think about it. Is somebody ready to jump in and walk me through it? Yes.
The vectors on the left side are additive to the vector in the center, whereas they're like opposing each other on the right. Or sorry, on the right side they're additive, and on the left side they're opposing each other, so they would sort of cancel out.
Exactly. So for example, if I want the velocity of the right side relative to the ground, that would be the velocity of the center of the right side relative to the center, plus the velocity of the center relative to the ground. We can double check that we got it right by canceling those inner subscripts, so that looks good. And I'm sorry, remind me of your name?
Claire.
Claire, as Claire just said, when we do it with this pair of vectors on the right, they're both pointing in the same direction. And so the resulting vector is something really long like this. So that would be the velocity of the right side relative to the center. Whereas on the left side, the two vectors are in opposite directions. So there's a partial cancellation. And so the result might be something like this, the velocity of the left side relative to the center. The difference is not as extreme as I've shown here, because the velocity of the center, the speed of the center is typically, I don't know, maybe 15 miles an hour, whereas the velocity of circulation is over 100 miles an hour. So there is a difference. And especially when you're talking about winds that are exceeding 100 miles an hour, an extra 10 miles an hour of velocity makes an important difference, but it's probably something like, let's say 140 miles an hour for the winds on the right versus 120 miles an hour for the winds on the left. But that's a big difference in terms of the damage that's done. Questions? Okay, we're going to shift gears a little bit and start talking about forces. And so there are some people in this class who are taking calculus concurrently with this class, which is certainly encouraged, allowed. And so we're putting off things that involve calculus for another week or so as to give you time to cover some of that material in your math classes. So we're not going to talk about things that move, but we can still talk about forces for things that are stationary. So that field of physics is called statics, i.e. stationary objects. And it's more complicated than you might think at first. So it's definitely worthy of thinking about carefully. And so let's think about some of the forces that are acting on stationary objects. So let's say if we think about my phone resting on my hand. So here's my phone. And here's my hand schematically. And we want to think about the forces that are acting on the phone right now as I just hold it steady. One of them, of course, is its weight. So a force is something that is trying to move something in a particular direction. So it's a push or a pull in a particular direction. And the units of force are called newtons. And so newtons. And we can break that down. We'll see exactly why it breaks down this way a little bit later, but it turns out that a newton is equal to a kilogram times a meter divided by a second squared. So it's sort of a strange looking combination of units. You don't need to worry about that too much right now. Just realize that force is measured in newtons when we're using the Système International for our units. So one of the forces that's acting on the phone as it sits on my hand is the force of weight. So we could indicate that on this diagram by a vector pointing down. So that's the weight vector. It turns out, probably not surprising to you, that the more stuff there is in an object, the heavier, the more its weight is. Or another way of saying that is that the weight is proportional to the mass of the object. So it turns out that the magnitude of the weight is equal to the mass of the object times the acceleration of gravity. We will talk about this in more detail later in this class, where this equation comes from, but for now it should make intuitive sense that if I have something that has a mass of 2 kilograms, it's going to have a weight that's twice as much as something that has a mass of 1 kilogram. This acceleration of gravity depends on what planet you're on. So on Earth, the acceleration of gravity is approximately 9.81 meters per second squared. It does vary somewhat depending on where you are on the planet's surface, because the Earth is not just a perfectly uniform sphere, but the variation is small. So in the context of this course, we're always just going to use 9.81, even though there are some places on the Earth where it might 9.80 might be a better number. We'll just always use 9.81. All right, so that's the force of, yes, Alex.
Does the weight account for the force of gravity acting upon the phone?
I would say rather that it's a description of that force rather than accounting for it. I don't know. Wouldn't be wrong to say it accounts for it. Okay. So far so good. Questions? If that were the only force acting on my phone, it would start to push it down, of course, but it doesn't. As long as I'm holding my hand there, it doesn't start moving. So there must be some force that's counteracting that so as to give a net zero force. Hopefully that idea makes sense to you, that if an object is at rest, there must be net zero force acting on it. That's actually part of Newton's first law. So Newton's first law, in part, No, let's not even go into that. Let's just say that for an object at rest, the net force must be 0. And hopefully that makes sense. The net, meaning the total force, must be 0. So there must be some upward acting force counteracting the force of gravity. So maybe if you have your phone handy, you can do this right now, or do it with a pencil or whatever. And you can probably feel, oh, I'm feeling something on the palm of my hand, right? So that means the palm of your hand is pushing upward on the phone. So that's the force that's opposing the weight of the force of gravity. It's called the normal force, N. So normal in this case means perpendicular, but we always call it in physics the normal force. It's perpendicular to the surface, the interface between my hand and the phone.
This came back from a search.
Force. So it's perpendicular to the interface between the hand and the phone. Perpendicular to interface between hand and phone. And we can think of it as the force from the hand. And since the phone is at rest, we can see that the magnitude and these two forces are pointing in exactly opposite directions. So the vector sum of them has to be 0. So n, vector n plus vector w has to be 0. Since they are point opposite directions, in this case, that means that they must have equal magnitudes. So the magnitude of the normal force has to equal the magnitude of the weight force. Now, what I have questions so far? What I've done so here is our first example of a free body diagram, which we'll be using a lot in this course. So a free body diagram, and you guys will get practice doing this plenty today, is simply a diagram of one object and the forces acting on it. And we're going to draw the forces as force vectors, with the length of the vector indicating the strength of the force. All right, so now let's do another example. Let's say, start with this same thing, but now in addition to those two forces, I'm going to start pushing with my finger to the side. But I'm not going to push so hard that the phone actually moves. I'm just pushing gently to the side, and I'm pushing it. I can feel the force that I'm pushing with in the tip of my finger, and yet it's not moving. So let's draw the free body diagram for that case. So now we're going to add a sideways push. So here's the phone. Here's my hand. It's holding it. So we'll put in the two forces that we already had, the weight putting down, the normal force going up. But now, let me just get rid of this label. Now I'm also adding another push like this. So this is the force from my finger, horizontal pushing. My finger is exerting a normal force. It's normal perpendicular to the interface between my finger and the phone. So it's a second normal force, but we'll just call it maybe F finger so that we don't get confused with the normal force from my palm. Now there must be something missing because the phone isn't moving, and yet the way I've drawn it so far, there would be a net force pointing to the left on it. So you have intuition. What is the other force that belongs in this diagram? Don't just shout it out. Think about it on your own. Check your thinking with somebody close to you. There's a force that's missing from my diagram. Okay, so I think I heard a couple of people that have a good idea about it. Who would care to take a stab? What's the force that's missing from the diagram? Yes. Friction. And so the friction, in this case, so I got everything lined up horizontal and vertical, the friction has to point to the right. So let's add that in. So the force of the friction, and we're going to use a lowercase f to indicate friction. It has to be opposing the push from my finger. So it's sort of opposing the motion of the phone and keeping it in place. And now we can see, aha, the horizontal force from the friction can cancel the horizontal force from my finger press, while the vertical normal force from my palm is canceling the downward force from the weight, resulting in zero net force. So we introduced a model for the gravitational force, that the weight force is equal to m times g. And I should have put a box around that, I'm sorry. We will be using this constantly, so that deserves to have a star around it. Similarly, we're going to introduce a model for the frictional force. This model is not, so the model for the gravitational force, this is sort of more or less exact, as long as you're not talking about, well, as long as you allow the gravitational acceleration to vary depending on your location. The model for the frictional force is much less exact because the interface between things can be pretty complicated. So this is a model for the frictional force, which is a good approximation for the case of rigid objects. So that means it wouldn't actually work so well for my hand because my hand is pretty deformable. But if instead, if I put this nice hard surface, those are two rigid objects, and so the model would work pretty well for that. And so it says the model is that the frictional force, and I'm going to put a little subscript on it for static, meaning this is the frictional force for the case that the object isn't moving. Next time we'll talk about friction in the case where the object starts to move. So static means for a stationary object. So F sub s is less than or equal to some maximum value. And the maximum value is mu sub s times the normal force. So mu sub s is called the coefficient of static friction. It's a dimensionless number, which typically has values between, let's say, about 0.1 and 1, but in some cases it can be larger than 1 if you have sort of very nicely oiled surfaces or something like that. It might be less than 0.1. So typically mu sub s ranges from 0.1 to 1. So it's interesting in this model that the frictional force depends on the normal force. Let's see if we can build intuitive understanding of that. So if I have this block here and I start to push on it, if I weigh it down, if I put a weight on it, so sorry, back up. I'm starting to push lightly and it's not moving. I push a little bit more heavily and it's still not moving. So let's think about what I just did. So light push. So now let's just think about a block on a table. And we still have the weight pointing down and the normal force pointing up. And we've got the force from my finger like this. So I'm pushing lightly. And we know that the frictional force must be opposing that because it's not moving. It's just barely touching. And now I push a little bit harder and it still isn't moving. So harder push. So we'll draw the same diagram. The same normal force and the same weight. But now the force from my finger is longer because I'm pushing harder. But it still hasn't started to move. I haven't started to push hard enough to make it move. So the frictional force has got to be greater to oppose the force of my finger. So this is telling us that the frictional force is variable. It's as big as it needs to be to keep the thing from moving. So that's why we have the less than or equal to in this equation, because it's variable up to a certain maximum. If I push hard enough, I can start to move the object. So now what about why is it proportional to the normal force? If I put a weight on top of this, let's draw that picture. So now I've got the block, I've got the table, and I've added on top of the block, there's a big weight here. Before we start thinking about the frictional force, let's draw the free body diagram for this without any pushing from my finger. So let's say that the block has a mass of little m, and the weight has a mass of capital M. And as a concept test with no pushing sideways from my finger, just like this, just sitting there, draw the free body diagram for the block. So this is the block. This is the weight that I'm adding, added weight. So as a concept test, I want you to draw the free body diagram for the block. Yeah, so remember that we only, in a free body diagram, we're only showing forces acting on the block, nothing else. As soon as you feel ready, you can start consulting with people in meeting. It's a little bit, maybe the first time you do this kind of a problem, drawing a free body diagram with multiple objects in them. So I think we'll walk through this together. So we still have the same weight of the block. That's still adding, that's still there. And maybe I'm going to be explicit that I'll put, that's the weight of the block. So that's a force that it's still experiencing, that the earth is pulling it down, just like before. But now it also is experiencing, so imagine yourself in the place of the block. I'm also experiencing the mass, this brass weight is pushing down on my head. And that's pushing with a normal force. The magnitude of it, of course, is equal to the weight of this brass thing, but it's not directly exerting a weight force on me, it's exerting a normal force on me, pushing on my head. So we could draw that like this. And in this case, this brass weight is heavier than the block is, so I'm going to draw it as a longer line. So this is a normal force from the block. It's a normal force. It is sort of indirectly created by the weight of the block. But if we think just about the forces that, okay, let's have me instead of the block, the force that I'm experiencing a normal force from this thing. And it would be pretty much the same as if somebody were pushing down on my head, right? It feels the same. If somebody takes an object that has the same cross-section and pushes down, I can't tell the difference. I just feel this thing pushing on my head. It's not a weight force, it's a normal force. It happens to be created by the weight of the brass mass, but is a normal force. Yes. It's a great question. Sort of essentially comes from, where is the force originating from? So there's a lot of new ideas that I'm introducing in today's class, and it's hard to get everything in there into a self-consistent way that will make more sense to you. So let's jump ahead and talk a little bit about the gravitational force beyond the model. So the gravitational force is caused by the interaction of let's say the atoms in your body through a long range force with all the atoms that make up the earth. They're pulling on you. So each atom in the earth is pulling on each atom in your body. And there's a lot of atoms in the earth, and there's a lot of atoms in your body. And so they're being pulled down together, and that's what you feel as your weight. So that same force, same kind of force is being exerted on this brass block. But when I think about the force that's being exerted on this wooden block, it has its own gravitational force, but then there's an extra press down caused by this brass block. So that extra press is not a gravitational force when we think about the force exerted on the wooden block. It's just a press down, which means it's a normal force. Another way to see it is that force is being exerted only right here in the center part, not on every atom of the block, right? So every atom of the block is being pulled down by gravity, but only the parts right underneath the brass are directly feeling that normal force. Yes.
I was just wondering, doesn't the atom weight itself have like a weight?
Yes, but, so it's a great question. Remind me of your name?
No.
Meg. So Meg asked, doesn't this have a weight force? And the answer is absolutely yes, but we are drawing a free body diagram for the block. And so we don't worry about the force on this. We only worry about the forces on the wooden block. Yes.
Why can't you combine the normal force of the weight and the normal force of the block and the flow? Cause isn't it? wouldn't it
So
be-
if I were to draw. Already forgot your name, sorry.
Sorry.
Claire. If I were to draw a free body diagram for the combined system of block plus weight, then I could think about the total gravitational force on that, but that's not what I asked to do. I asked to do just a free body diagram of the wooden block. Yes, Dylan.
So if there's double, it's not double, but I guess if there's more force acting down, does that mean there's more force acting upwards as
Yes.
opposed to static?
Absolutely. We haven't gotten to that yet, but it means that the normal force exerted by the table has to be bigger. Let's go ahead and add that in now. I know there's another question hanging out there, but we've got all the downward forces. The normal force that's acting upward has to be like this, so we could call that the normal force from the table. And the vertical forces have to cancel, so the normal force from the table plus the normal force from the block plus the weight of the block. All those have to sum to 0. We know that these two forces oh, geez, sorry. I was bad about notation. So I wrote normal force from block, but what I really meant was normal force from the weight. I should have picked, this should be from the weight, not from the block. Sorry. So we've got a block, we've got a weight. So this should be the normal force from the weight here. All right, so the normal force from the table plus the normal force from the weight plus the weight of the block have to vector sum to be 0. These two are pointing down. This one points up. And so that means in terms of magnitudes that the normal force from the table has to have the magnitude equal to the normal force from the weight plus the weight of the block. Sorry about the confusion. Okay, there's somebody else over here who had a question.
About the from block thing, so.
Okay. Okay, sorry. I think I've confused you enough that before I start talking again about friction, I want to do another example that just involves normal forces and weights. Do this example. So I'm going to take my phone and I'm going to push it up against the ceiling. So I'm pushing up. It's not moving, but I'm pushing up with a little bit more than its weight. Draw the free body diagram for this.
Oh. So you're.
So pretend my hand is the ceiling. We'll do this in a little safer way. I'm pushing up like this, but it's not moving. We want the free body diagram of the phone, yes. So if you're ready, you can start talking it over with people near you.
When you're done. The two buttons for the phone, and then that's it. My wagon, you got it, I think it's you.
No, separate. Yeah.
And then. Yeah.
So, so far so good, but you don't have the relative value. Eventually, when we start talking about, there will be a point where we can air and where the force applies. So far so good, but maybe looks like the next force is down.
I think that the ceiling in the neck, weight and the ceiling, but then your the weight like your building has.
So far. Yeah, not quite. So far, like the next is pretty down. Oh, I see. Okay. Let's talk about this together. So I'm going to start by drawing a picture. Here's the ceiling. Here's the phone. And then here's my hand. Like this. Sarah, can you walk me through it, please?
So I said that there was, the weight from the phone going downwards.
So there's a weight force on the phone. So that's the force being exerted by the earth pulling the phone down. Good.
Against the ceiling exerting the normal force downwards too.
So there is a normal force at this interface between the ceiling and the phone. So that's downward. So maybe I'll draw that like with that length. Okay.
And then there's a force from the hand pushing against the ceiling, so going upwards, and that the magnitude of that force is equal to those two downwards.
So I haven't quite chosen my scale correctly, but let's call this the force from the hand is pushing up, and the magnitude, what Sarah just said, is the magnitude of the force from the hand has to equal the combined magnitudes of the normal force. This is from the ceiling and the weight force. Yes.
How do you determine notation between just a force or a normal?
They're all forces.
What I meant is using N as a
Oh.
normal force. Why would the force upward
It's so the force upward is also a normal force. So the force that my hand is exerting is a normal force. So it's up to you to invent a notation. So I could have done it the other way around. I could have called that N, and I could have called the force from the ceiling F ceiling. That would also be completely correct. So I would say most of the time, and this is just a slight convention, that if we have sort of passive things like floors and ceilings, that's where we usually use the term normal force, whereas active things like hands and fingers, we will use some invented term for that. Great question. Other questions? Okay, so now let us return to, try to be careful with the words, our block and our weight. And let's think, so let's go back first to the case where I'm pushing it, and eventually it starts to move. The harder I push it, eventually I'm pushing it with enough force to move. Now, when I put the block on it, use your intuition first. In order to get it to move, am I gonna have to push with the same strength as I did before, or more, or less? How many people think the same? How many people think more? How many people think less? So some people were unwilling to raise their hand, so don't do that again. You always, when I offer you that choice in the future, you must pick. It's fine to be wrong. It's not fine to not pick. But most of you have the right intuition. Of course, if it's something heavier, you got to push it harder to get it to move. So that's, let's draw the comparative free body diagram. So here's first our block without the weight on it. So resting on the surface. It has its own weight acting down. It's got the normal force from the table acting up on it. Now, when I add the weight to it, whoops, draw it the same way. I'm gonna add, so here's the same block, and we'll add the weight on top of it. As we just talked about, now there is the weight force. There is a normal force from the brass. Let's call it from the brass. So this is the brass weight. Normal force from the brass acting downward. And then there is this now larger normal force from the table acting upward. So the normal force from the table has the same magnitude as the combination of the normal force from the brass weight plus the weight of the block. So the normal force from the table is now larger because I put this brass weight on it. And so remember our model for the frictional force, that the magnitude of the frictional force is less than or equal to the coefficient of static friction times the normal force. So that's now saying because the normal force is larger, the maximum frictional force is now also larger. Questions? Okay. So let's see how far we can push this today. Let's try doing things where the forces are not all perpendicular to each other. So let's go back to the simple case where we just have the block on the table. But now, if I were to push straight down with my finger, that would be pretty much the same as having the brass weight there. But now I'm going to push at an angle with my finger, like this. And I'm not pushing hard enough to move it, but I'm pushing downward and to your right. And I want you to draw the free body diagram for that. So I'll sketch the situation. So here's our block and the table, and here's my finger. And let's call this force from the finger is going to be like this, F finger. And if the block is not moving, draw the free body diagram in this case. As soon as you feel ready, you can start consulting with people near you.
Very big, normal force, and then that's Down a lot.
Let me, some of you already have this intuition, but I should have said it more carefully. Friction always acts parallel to the interface. So the interface here is a horizontal interface, and so the friction is going to be horizontal. So there's no vertical component to the friction. Keep on talking.
No, I agree. Like, definitely, you know, I just. I like to.
You don't know.
Okay, Sadie. Walk me through it, please. Go ahead. Sadie, go ahead, walk me through it, please. Okay, so I could resolve this into components. So let's call this component F finger sub Y, and this one is F finger X. Not quite. So let's add in the weight force first. Right, so there's a weight force downward like this. And now there is a normal force from the table, but it's not just equal to the F finger Y. Instead, it's equal to, yes. So the normal force from the table would be upward like this. And maybe I'll explicitly say from table. So that the normal force from the table, that's the only upward force in the problem. And so that's going to have a magnitude that's equal to the weight plus the Y component of the finger force. So Sadie has done a great job with talking about the Y components. let's finish talking about the X component. Somebody else can jump in. Yes, Anquan. Yes, which direction does the frictional force point? Yes, there has to be a frictional force pointing this way. And how does that relate in magnitude to anything else that I've already drawn? Yes, so the frictional force points to the right. And so it's going to be equal in magnitude to the X component of the finger force, which is pointing to the left, so that the net force is still 0. Good questions. All right. Let's try starting on the next idea, which is related to this. And we'll see how it goes. We're not going to finish this in the 5 minutes we have left, but this is Newton's third law. Just getting started on it. What it says is that if object A exerts a force on B, then B exerts an opposite force on A. And so, for example, take your finger of one hand and press it against the palm of your other hand. What you should feel is in your palm, you can feel there's this pokey thing poking into my palm. That's the force from your finger poking into your palm. But in the tip of your finger, you can also feel, oh, something is smushing me. That's the force of the palm smushing up into the finger. So if we were to draw that, here's the finger of one hand, here's the palm of another hand. The force that the finger exerts on the palm, F finger on palm, is opposite to the force that the palm exerts on the finger. So I'm going to draw two separate free body diagrams. On the left, I've got a free body diagram for the finger. On the right, I've got a free body diagram for the, on the left, I have a free body diagram for the palm. On the right, I have the free body diagram for the finger. So this is the force of the palm on the finger. They're opposite to each other, so they're equal in magnitude. Force of the finger on the palm has the same magnitude as the force of the palm on the finger. Notice, really important, these two forces, which are sometimes called an action-reaction pair, do not ever appear in the same free body diagram. I have to draw two different free body diagrams because they're being exerted on different objects. So this is like the most common error that beginning students would make, is to try to put those two into the same free body diagram. So the two forces in Newton's third law which are sometimes called the action-reaction pair. So the old way of saying it is for every action, there is an equal and opposite reaction, but that's too confusing. So appear in separate free body diagrams because they're exerted on opposite force objects. On different objects. So let's go back to the beginning and do the sort of simplest possible case where we have the block and the table. And we're going to draw separate free body diagrams for the block and the table. So the block we already know has got the weight force and the normal force from the table. That's canceling out the weight force. If I draw a separate free body diagram for the table, so this is the free body diagram FBD for the block. Over here is the FBD for the table. And there, we're not worrying about the weight of the table for now. So, but there would be a normal force from the block that's acting down on it. And sometimes I might draw a kind of dashed line connecting those two diagrams to indicate that those are an action-reaction pair. Now notice so far, there's an unbalanced force acting on the table. And so you would think if that's the only thing going on, then the table would start moving down. But of course, this force is pushing up on the table from the ground. We're not going to worry about that right now. So this is incomplete. Questions so far about this? We will definitely hit this a lot more on Monday. Okay, thank you.